My name is Rasmus Bro, and I am going to teach this course on Principal Component Analysis, or PCA as it is usually called. This first part will be about some background information on why and how PCA is useful, and then we will discuss a little bit the theory behind PCA, and finally treat two very important parts of validation, namely choosing the number of components and how to perform outlier detection. Let's start with a simple example of how the brain works. If we want to recognize a face, we usually don't look at variables one at a time. Let's have a look at one variable or one feature below, the nose, and try and figure out who that person might be. That's not very simple in this case, but we could look at another feature or another variable instead. For example, the eye, or we could look at both simultaneously. And even though it helps to look at both, it's not really simple to see which person it is. But if we look at the whole image, there's absolutely no problem. It's quite simple to see who it is. So, the brain does not look at individual features. It doesn't look at the levels of the individual features, but rather it looks at the relations, all the different relations between different features. And we would like to have something similar when we look at data in different problems. Let's take a more realistic example. Here we show the height of different humans and different monkeys, and we would like to be able to distinguish these two groups. And even though we do see a tendency, it's also very clear that we cannot have a cutoff level at some level of the height that will help us perfectly separate the two groups. We could try and add another variable, for example the weight, but we see that the problem is exactly the same. So does that mean that these two variables cannot be used to separate the two groups? Well, let's try and see if we can find a way to look at the pattern of these two variables. One simple way to do that would be to simply plot the weight versus the height. That way we get not only the levels of the individual variables, but we also get the relation between the individual variables. And as you see here, we now have a perfect separation just by plotting the height and the weight against each other. So this is the kind of pattern recognition that we are looking for when we do PCA. That way we can extract more information from the individual measurements than just the individual measurements. This is a very important principle, and you're going to see that it will be useful in many different kinds of applications. So we will try to see how we can formalize this even when we have more than two variables. Another example, and an example on how this principle is used, for example, in process monitoring. Here we have a variable measured at different times, the temperature, and we can see that it varies between 25 and 50 degrees. So that's the normal range for this process, and as long as all the measurements are within those limits, the process is said to be in control. We might have another measurement, for example the pH value, and just as for the temperature we can see that there is a certain level of normal variation. So for both of these variables we would say that the process is in control. But if we plot the two against each other, we can see that maybe that's not the case. Some points, well, they are within range for both temperature and pH, and they also have the same relation between temperature and pH as the other ones. But for this one red measurement, even though it is well within control for both pH and temperature, the relation between pH and temperature is broken, so clearly there's something wrong here, something that needs attention. This is a very useful concept, for example, in process monitoring, but also, for example, in medical diagnostics and a number of other situations. So we want to extend this principle because in some applications we might not have 2 variables, we could have 3, 4, 5, or we could even have hundreds or thousands of variables, but we want to be able to look into that many variables and see patterns of variations. Here's an example of what is actually a quite simple data set. We have different countries, 49 altogether, and then we have 7 demographic descriptors of these variables. The number of infant deaths per 1,000 births, number of inhabitants per physician, etc., etc. So this is a fairly small data set, but even that can be complicated to look into. And what you will see is that data in itself is not the same as information and understanding. When we have a data set like this, we want to figure out how all the different variables and all the different samples compare to each other. How do different countries differ? What variables are related to each other? What samples are related to what variables, etc., etc. Some very simple questions that one could ask for these data would be, for example, what European country is most similar to Japan? What country is the most strange one? These are very simple questions, but they're difficult to answer from the data. One important note here is that when we ask questions like this, or when we do data analysis in general, well, we are getting answers in terms of the data that we have. We are building empirical models based on the data that we have. So in this case, for example, we are not doing an exhaustive analysis of what differs between different countries. We are only doing that with respect to the variables that we have included. So this has to do with relevance of the data, which is outside the scope of this course, but it's a very, very important aspect to have the right data, that you know that those are relevant for the problems in question. So we will start out here simply by doing a PCA analysis and then see what comes out of that. And in order to illustrate what PCA is, let's first look at a slightly simplified example where we look at a small data set of 3 variables only. That will help us graphically show what's going on in the data. In the next slide you will see the movie that visualizes PCA. If you have problems running this movie from inside the PowerPoint presentation, you may also go back to this slide and download the movie from the web. Then you can save it on your computer and view it, for example, in Windows Media Player. Here we see a table of data. 5 samples and 3 variables. Every sample can be represented by a 3-dimensional coordinate system. If we look at Smith, he has workload 1, so we can add a point 1 on the green axis representing Smith's workload. And if we plot the coordinate system in a normal fashion, we see that every sample, just as Smith here, will be represented by 1 point. And we can add all the remaining samples in this coordinate system, and that way we get an exact representation of what we know, the data table, our data, in this coordinate system, which could have had even more than 3 variables, but then we would have difficulties in plotting it. But we see that we can represent our data in a coordinate system without losing any information. If we look at these data, even though they are described by 3 variables, we can see that they almost only vary in 2 directions. So instead of using the original 3-dimensional space, we can represent the data by a plane that will well approximate the data. In this case, we don't save a lot of variables by that, but if we had more than 3 variables, this could be a substantial saving. The way we determine this plane is in a least square sense, and as you can see, if we had oriented the plane differently, the distance of the points to the plane would have been much larger. So there's a well-defined way of defining such a plane. We can also project the original 3-axis into the plane, and that way we can see how the different directions in the plane are influenced by the different variables. And this is the biplane. In the final plot of the movie that we just saw, we saw a plane. That plane was describing what happens in the bulk of the data. That plane spanned the main variation in the data. The plot is called a biplot. It's called a biplot because it gives us a description of both variables and samples in the one and same plot. And if you have 2 points that are close to each other, for example 2 samples, well, that simply means that these 2 samples are very similar with respect to what the plane is describing. So if that plane is describing most of the variation in the data, we can say that these 2 samples are very similar. On the other hand, if they are oppositely placed, well, that would mean that they are very dissimilar. When one is high on a certain variable, well, then the other one is low, and vice versa. The same goes for the variables. 2 variables that are close together, well, they contain more or less the same information. And a sample which, for example, is close to one variable, well, that indicates that that particular sample has high values for that variable. We will see more interpretations of this plot in the next slides, but it's a very, very important plot because it contains all the essential information of the PCA model. In some situations, though, we don't have just a plane or a 2-dimensional reduction of our data. Sometimes we need 3 directions, 4 directions, or even more. But what we always aim at is to have as few as we can possibly do with. Here we have the results of doing a PCA on the demographic data. First, we show only the score values, so we have a score plot. And on the axis you can see how well these 2 scores describe the data. In this case, we are explaining 74% of the data, so that's quite good for data like this. And that means that any interpretation that we make in terms of this plot will be descriptive for 74% of the variation in the data. And of course, the first thing we note is that there are 2 countries that are very different from the other ones. And that means we have actually already answered one of the initial questions. If we want to see what samples are most different or most strange, well, that has to be Singapore and Hong Kong. We don't know exactly why they are, but they are clearly different from the other ones. This is an example of outlier detection. Singapore and Hong Kong are outliers. Outliers meaning that they are different from the bulk of the data. In PCA we often, though not always, assume that our samples come from a certain distribution, not necessarily an easily statistically described one, but at least that the samples are similar in nature. But in this case we can see that PCA is not really modeling the variation among all the samples, but it seems that it's rather modeling whether we have Singapore or Hong Kong or not. And that's usually not what we want to do with a PCA. We want to describe the common phenomena in the data, not individual peculiarities. So, in a simple score plot like this, we already get an indication of whether a sample is an outlier. And this is exactly how it's used, for example, to detect whether a process is running appropriately or whether the process is going out of control. When we have detected samples like that, like Singapore and Hong Kong, or outliers in general, we want to understand why they are outliers. And the loadings will tell us what the reason is for these samples being located where they are. The loadings provide us the information about the variables, and we can put them on top of the score plot to get the biplot that we also saw before. And if we do that, then we have all the 49 samples plus the 7 variables in one plot. And the interpretation is exactly as explained earlier. So we can now see that Singapore and Hong Kong are special because their population density is very different from all the other ones. The population density also differs in the other samples, but not to the extent that it does for Singapore and Hong Kong. So not only do we get information that Singapore and Hong Kong are outliers, we also get an explanation for why they are. And in this case, we would probably say, let's remove Singapore and Hong Kong because they are really disturbing the analysis. An important note here is that you will realize that Singapore and Hong Kong are not incorrect samples. They are not wrongly measured. They are simply just extreme, and they don't fit together with the other ones. And the decision as to whether they should be excluded from the analysis or not, that has to come from your knowledge about the problem, whether you need to have a model that describes everything or whether you want to describe only the major part of the data. Quite a number of things can be seen for this specific model. If you look at the scores and the loadings, you see, for example, that all the variables are quite important because no individual variable is located near 0.0. If there had been a variable at 0.0 or close to that, that would mean that that variable was not consistent with the major part of the variation in the data. We also see that many variables are correlated. For example, the gross national product and the number of students, those two variables are located close to each other, and that means that they contain more or less the same information. So, for example, if one was very expensive, we could say, let's take the other one and exclude the expensive one in order to save some money, and we won't lose much information by doing that. We can also see that the gross national product is oppositely located to, for example, infant death, and that means that countries with a high gross national product will have a low infant death. We can also see, for example, for the samples, that India is located in the lower left part, and that means that they have the most serious health problems, whereas USA is the country that has the highest economical factors. If we look at the PCA plot when we have excluded Singapore and Hong Kong, it's easier to see the different details in the data. And now we can start to look more detailed into the patterns, into what countries are grouped together, for example, and we can make some quite interesting observation. When we look at the data, we can see that, well, we have a health direction and a money direction. Those are names that we could attach to the Indian direction and the USA direction. But we also have a third direction, and in this case we can call it an island direction. We see that we have small islands mainly in that direction. So even though this may not be the best example, this does show us how we can do exploratory analysis. And that is that we can learn something from the data. In many traditional types of data analysis, we are usually trying to do hypothesis testing. So we have an initial hypothesis, we generate data to verify or reject that hypothesis. In this case, we're not doing that. We are taking a data set that we believe is relevant for describing some problem. We analyze the data, and now we actually see and learn something new from the data, something that we hadn't thought of, but which is empirically observed to be in the data. So we see that we can generate hypotheses directly from the data, and that's exploratory data analysis. We also, by the way, get an answer to the other question that we posed initially. Which country in Europe is most similar to Japan? Well, we can see that that would be the Netherlands or Belgium. And you see that those two questions that we posed initially, which were quite difficult to answer from the data table, are very, very simple to answer when we actually just look at the plots. Another strong feature in this visual approach is the use of markers. In this case, we have exchanged the sample names with colors, and we use colors for poor and rich countries, and then it was a little bit unclear where the Eastern European countries should be positioned, so we used a specific color for the Eastern European samples. And you can see here that, as expected, the leftmost countries would be the ones which are poor, and the rightmost, pointing in the economical direction, would be the ones that are rich. And the Eastern European countries are in the middle of this, sort of going from poor to rich. If you have external knowledge about your data, you can have many types of external knowledge, different batches, different groups, different whatever. Well, you can use that external information when you do your plotting, and that can help you detect groupings in your data that would otherwise not be simple to detect. And this is a very useful approach when you have large data sets or you have many types of variation expected in your data. Until now, we just visually looked at the PCA model, but it is important to note that it is a quantitative method, and you can have numbers out for all the different aspects of the model. You get scores, you get loadings and residuals. The loadings define the new coordinate system, defines the plane in case we have two components. So each loading is a direction in space with numbers associated to it. And the score is then simply the amount of that artificial latent variable for a particular sample. So for every sample we have a score value for every principal component. And you can extract all these numbers and use them in further analysis for clustering, calibration, or whatever. So this initial example hopefully has shown that it is possible to handle many variables simultaneously in a rational way, and also that you will get more information by doing that instead of looking at the variables one by one. And that means that you can overview, diagnose, monitor, predict, classify, even having complex data. And it also means that you can learn about a problem from data describing the problem. You do not need to know everything beforehand, and in the extremest case, you do not even need to have an hypothesis. If you have data that describes a problem, you can look into those and see if there's any useful information about your problem.